have names for everything. What are you talking about?
Stop sharing. Alternative between, do you know this completely esoteric concept and do you know how to multiply two matrices?
The big statement about computation, the statement about the.
Yeah, there were a lot of philosophical statements also.
I think at some point what did he say was something like,
This is being recorded.
Good morning, everyone. It's a pleasure to have Chaitanya Agarwal as the speaker today. Chaitanya is a PhD student at NYU, and he did his undergrad previously from IIIT Delhi and also a master's from NYU. And his main research interests are in the area of programming languages and verification of security applications. So for me, for a while, Chaitanya was like, he used to exist like virtual. And it has been, so I was talking to him almost for a year before I could meet him in person. And so, yeah, it's good to see you today in PIFR. So, yeah.
Yeah, thank you so much. It's good to be finally here. So I'll just start with the talk. I'm going to talk about verified programming frameworks for authenticated data structures. So this is joint work with Simon Gregerson and Joseph Tassoretti, my advisor. Okay. So what are authenticated data structures? Assume we have a large public key value store where individuals can share data with everyone else. And here we have Alice who wants to fetch Bob's value. This database returns V to Alice, and now Alice wants to know if V is indeed Bob's value or not. Right. So to solve this problem of trust, there are these authenticated data structures where one entity, which is called the prover, stores the entire data structure. In the previous example, the left side thing was the prover. And everyone else is known as the verifier. So Alice was a verifier. And they have.
Could you go to the previous slide where you said the left one side is the prover? So here is the.
Yeah. So this database is the prover. This database is storing the entire data structure, and we call this the prover in this.
So why do you call it a prover? Just because it's storing the.
So it will be clear. Yeah. Everyone else is called the verifier, and they have a small digest, also known as the commitment of the data structure. Right. Now, any function over the data structure that the verifier may want to be computed will be computed by the prover, who produces a cryptographic proof along with the output value. And the verifier can check if the proof and the output value are consistent with its copy of the commitment. Right. So let me show you an example. This is known as a Merkle tree. It's one of the most common authenticated data structures example used in practice. And it's essentially an authenticated binary tree, right? It's a key value store where all the values are stored at the leaves. So S3, S4, S5, and S6 are the values. And the keys to these values, for instance, for S3 is the path to S3. So for S3, the path is, the key is left and left. For S5, the path is right, left, right? These are keys and values. In a Merkle tree, every local node and leaf, in addition, has an associated digest. For leaves, this digest is computed by computing a hash of the value. So D3 is hash of S3, and so on. D5 is hash of S5. Right? Now here we assume that the hash function is collision resistant, and that means that it's hard to find two strings with the same hash output. Okay. Now for nodes, for instance, for D1, this digest is computed by taking a hash of the concatenation of D3, D4. Right? So D3, D4 are strings, we concatenate them, compute their hash, and that's D1. Right? And so on. So the commitment for a Merkle tree is the digest of the root node. Right? So let me show you an example of how the prover and the verifier interact with it, and you'll understand why it is constructed in this way. So say we have a simple fetch query where the prover is asked to fetch the value at right comma left, that is S5. Right? So now the prover has to return the value and also return a cryptographic proof for this. So what the prover does is that it to the proof stream, it adds the digest of the opposite node it's going to, right? So it goes here first. So it adds D1 to the proof stream. Then it goes left. So it adds a digest of the right node to the proof stream. Right? And finally, when it reaches here, it just returns the value. So this is the proof stream and this is the value. Okay. And let's see how the verifier uses this proof stream. So first of all, remember the verifier doesn't have access to the tree. It only has D0. Okay. And now it has this proof, and here's what it does with the proof, right? So first of all, the verifier has S5. So using S5, it can compute D5. Then using D6, which it gets from the proof stream, it can compute D2, and finally it can compute this D0 prime. Okay. And now if this equality holds, that this digest constructed using this proof stream matches the digest that the verifier already has, then the verifier can note that this is consistent with this commitment, right? So
So Alex has D5 already, you said.
Alice can compute D5 using S5. Alice gets this and S5.
Sorry, yeah, okay, right.
Yeah. Yeah.
Got it.
Right. So now Alice can know that S5, as long as this holds, that so assuming D0 is correct, right? I haven't really said that how Alice gets the correct commitment. I won't talk about that. But assuming D0 is indeed correct, then if this equality holds, then Alice can know that S5 is the correct value, right? There's a very small possibility of a hash collision. We mostly ignore that because it's extremely unlikely. So if this equality holds, S5 is correct. Conversely, if this is false, then S5 is definitely false. Okay.
So hash function is a public function.
Yes, the hash function is public. That's true. Yeah. So now they find use cases. A lot of applications they're used for implementing certificate transparency in all our browsers. They're used for key transparency in applications with end-to-end encryption. They're used for binary transparency, protection against memory corruption, and so on. Basically, whenever there is some value distributed over the internet, you want to check its integrity, right? So now what this talk is going to be about, it's about verified programming frameworks for ADSs. So what we want to do is that we want to make sure that the proof handling operations for the prover and verifier are implemented correctly, right? These are important. We have seen that it's like these are used in important use cases. It's important to get the implementation correct. And what we are going to talk about is that we're going to propose programming framework for these authenticated data structures, such that at least the proof handling operations, where the prover generates the proof and the verifier verifies the proof, these operations are implemented correctly. Okay, so to do this, I'll first describe this work Lambda Auth by Miller et al. In 2014, where they give a DSL to implement this, right? This Lambda auth will basically be used to give some sort of an algorithmic intuition of this framework. Then I describe Authenticate. That's a library implementation of Lambda auth, which was proposed by Bob Atke later on. Arguably, this is a better programming framework than Lambda auth, and I'll describe later why. And finally, I'll describe our work that appeared in CCS last year, which gives a formal proof of correctness of Authenticate.
So, can you say a bit more about, maybe you already mentioned, that what is meant by that these proof handling operations are implemented correctly?
Yeah.
So, are there some specifications against which you are?
Yes, the specifications will only make sense when I describe them later.
Okay.
But what I want to say over here is that sort of limit the scope of this. So I don't want to say that if someone uses this library, then their fetch operation will automatically be correct. I only want to say that the proof generation and the proof verification process are going to be correct. Right. Also, I've not explained a lot of other details about authenticated data structures, like for example, how the commitment is distributed and how they're actually used. There's a lot more things that are going on there. I only limit myself to the prover and the verifier operations, the core. But Like I can just say that this operation is also very vital in any authenticated data structure implementation. Yeah.
So, what do you like? Can you explain that domain specificity thing, means? Like,
So we call this a domain. So domain specific language is like usually you have. So what we'll do over here is that we have this OCaml language, and we make some changes to OCaml so that actually Miller et al. Miller, they made some changes to OCaml to specifically serve this authenticated data structure use case.
and your class of authenticated data structure is fixed. Like, have you?
Yes, so there is sort of, we say that this is, so like this will make this clear. So they first of all realize that the prover and verifier binaries can be compiled from the implementation of a non-authenticated data structure, right? So for example, for a Merkle tree, the non-authenticated data structure is a binary tree, right? So what this does is that if you implement binary tree and all the fetch and the update operations, you pass it through their DSL, this extended version of the camel compiler, and this will return prover and verifier. Right. So to answer your question, there are other forms of authenticated data structures as well, which are more sort of which involve some exponentiation, like addition and so on. So they are not going to be covered by them. I haven't described them, but these sort of Merkle trees or skip lists, or basically this data structures that you can like sort of more structural data structures. I don't exactly have a name for this class. They are going to be covered.
No, so like, I think that's what I was trying to clarify. So the domain in your DSL, does it refer to the class of data structure that you're looking at, or the programming language that you are going to?
Domain here is the like, it's not about class of data structures. It's a more generic term to say that I'm thinking about authenticated data structures. So say someone is say someone can make some changes to OCaml so that it becomes better for a particular application. So this is not about a class of data structures, it's just about the application, the use like the use space that we are talking about. So that's called a DSL. Maybe this becomes clear as I describe this language, it will become clearer. So
What is
basically,
generic about this?
sorry.
Why is it generic? What is generic? Since are you, what are the other data structures other than
I can do any data structure. I just gave the example of the Merkle tree.
But you also said that data structures it can't do, like some experimentation.
So, like a class of data structures, maybe. So, I'm like, I don't even understand those data structures very properly. So, these are used in multi party computation and they're more cryptographic in nature. I'm not going to talk about them at all. But
Is there a definition of the class or?
I haven't found a good definition either. But from what I can tell you, like there's a big enough class where I can also use generically. Yeah. Right. Okay. So what Miller et al. Do is that they extend the OCaml language with 3 new primitives. They extend this with authenticated types. This is denoted by auth. This says that any object that has type auth denotes the type of the authenticated version of that object. Then you have these auth and unauth primitives that convert the converter value to its authenticated version and vice versa. Right? So each of these is interpreted differently for the prover and the verifier. And now what a developer can do that who wants to implement authenticated data structures is implement code like this. So this is some function programming language code. So they can implement some code like this, which I'll tell you in a moment, which almost looks exactly like a binary tree fetch. And once you give this code to their compiler, you'll get the prover and the verifier implementations of the Merkle tree. Right? So this fetch, this type tree over here, this is a sum type that essentially says that it is either a string, so this is either a leaf, or this is a binary node in the middle. And here I have implemented the fetch operation. This takes in authenticated tree, right? And it it basically doesn't. So this is pattern matching. So this says that if this list is empty, it goes to this case. If this list has some values, it goes to these two cases, right? And Point is that yeah, here we call, so this is, since this is an authenticated tree, here we have to call an unauth to convert it to type tree so that we can do this pattern matching over it. Right? Point is, if you remove this auth, all this auth and unauth from this code, this is binary tree code.
So when you say this auth part, so
Yeah.
does it indicate those that the D that you were talking about?
I'll just tell you what it means exactly in the next slide. But yeah, sort of like a node in the middle is composed of two authenticated trees, not trees now, in this case, in this setting. Right? What I want to tell you from right now is that if you remove auth and unauth, this is simple binary tree code, and you can use this code to implement your Merkle tree. Yeah.
So Miller's paper is based on OCaml,
Yeah.
but is there anything fundamental about OCaml that we have to stick to? Like,
I'll come to this later.
like there is something about OCaml.
Not exactly. There is a class of languages that is more important. I'll come to this later.
Why are you turning them left and right? Why is they not just leaf and normally? Like that kind of-
So this is just like I can use anything here. I can
So
use leaf. I can
The
use
data
whatever.
structure you were making that, I mean, the abstract data structure that you are making by using these constructors, like when
Yeah.
rice or camel.
So basically, when we define the sum types, we have to define like these names over here. Like this name can be
You
anything.
could have called it leaf offstring and
No,
internal of
My question was, why didn't you do it? Was there something that I'm missing?
There's a very, very particular reason why I use left and right. It won't be clear right now. Okay. So let me show how these, like why this is constructed this way. Like how these types are interpreted. So when the program is going to be compiled, a auth for the prover is going to be interpreted this way. So it is going to be interpreted as a tuple, where the first value is the object itself, and the second value is the digest of that object, computed that way, computed by taking a serialization and computing a hash over it. Right. So when this program is compiled, tree auth is going to be changed to this tree, comma, digest of tree. Okay. For the verifier, it is only going to be digest of tree. For the, like, you can also assume there's an ideal program that doesn't do any authenticated operation, that just treats it as a plain binary tree. For the ideal, it's just going to be the object itself. Okay. The auth primitive for the prover and the verifier will produce the respective authenticated type. And the unauth is where the magic really happens. So the unauth is going to produce the unauthenticated type. For the prover, it is very straightforward. But it's also going to add a serialization of 8 to the proof string. Right? So I'll go to this later. Let's see what it does actually. So here's how this prover Merkle tree code looks like when we compile it using this Miller way. Okay. So first it is going to call an unauth on this node, right? And then it adds a serialization of that node, that is D1 and D2 to the proof string. Right? This is different from the proof I showed you earlier, the proof constructions that I showed earlier. But to get this sort of structural property, we have to do it this way. So then it adds D1, D2, then it adds then it adds D5, D6, and finally adds S5. Well, finally returns S5. So this is the new proof string that is being constructed by the Miller et al. Sort of version. Okay. And now the verifier is going to read the serialization. The verifier's job is to consume the proof stream and verify the proof stream, right? So the way the verifier does it in this way is that it reads the serialization. The guarantee sort of is that the both the prover and verifier are running the same piece of code, like same algorithmic piece of code. They'll call unauth, the verifier and the prover will call unauth on the same objects at the same time. Right. So whenever the prover is computing auth, say on that one, the verifier is also going to compute on this unauth on the same node. Right. So what it will do is that it will read a serialization, read the object from the proof stream. It will compare its hash with its copy of the digest and deserializes it to get unauth type. Again, it's best explained through an example. It has D0, again, the verifier only has D0 at this point, and it has this proof stream. right? So now it will compute, it will do unauth over D0, and unauth over D0 is supposed to correspond to D1, D2. If this hash function is fine, if this equality function goes through, then the verifier knows that this is fine, that this value that the prover has added indeed corresponds to it indeed corresponds to D0. Now it can use D1, D2 to get like that. It will use use D1, D2 to get the digest of the two children. So this it can do with some deserialization. It sort of knows how this D1, D2 string was constructed, and it also knows how to deconstruct it to get the individual digests. Right? So let's just assume that it gets D1 and D2. Similarly, now it calls unauth over D2. It will again do the same hash, and yeah, this rest of the same. Yeah.
D2.
So
Yeah, I don't understand how you got D2.
so you have D1, D2, right?
But
That's a single string, that is true.
you know where the concatenation ends.
Sort of, yeah. Like we know the serialization and deserialization functions are sort of agreed upon between the prover and the verifier. Okay. No, so now basically this is a different way of computing the same operations that I showed you initially. But in this operation, we are getting this ease of implementation. You only have to implement the binary tree operations, and you get all of these checks for free. The verifier doesn't have to explicitly implement how these checks are being implemented. There are more checks because of that, because of this ease. The verifier has to do more, like the computation on the verifier side ends up having to do more of these checks. But yeah, that's sort of the benefit of this, that the verifier doesn't have to worry about how to implement these things. They're correct by construction, sort of.
But there's a issue that I'm seeing is that if your tree is long enough,
Yeah.
wouldn't the failure probability start killing you slowly?
So it's like the failure probability. I think you mean by that is the collision probability that hash.
Yeah.
So typically a good hash function's collision probability is 10⁻⁻, -70. So if you assume a tree of like depth 30 even, which can store a lot of values, billions of values, that's still mostly okay. And you can construct a better hash function.
But even theoretically, the assumption is for collision resistant hash functions is that the probability of you being able to engineer a collision is smaller than every inverse polynomial. And you are just fighting against polynomially many hash things, so you can afford the union problem.
No, I was thinking more about you get different branches of the tree, right? So it's not so all possible paths you will have to fight against, right?
But that is just the number of leaves, right?
Yeah.
But for the number of the number of leaves is going to be the number of red leaves solve all this, right?
The number of paths is just a number of bits when you're polynomial time.
Yes, you have polynomial type, the polynomial plane.
Right?
But this unwrap, so not unwrap, this unauth for the verifier has to be called on the auth type as in the prover code, right?
Yes.
Because
Yes.
it's not the auth type for the verifier code. So I'm getting confused because this sort of seems like, why not have two types? One called auth, maybe because then you have to write two different codes.
Exactly.
So you're just saying that somehow we have this type alias, and it's just that in two different contexts, it can be compiled with two different backend type definitions.
Yes. Yeah. So
And then probably you need some axioms. The only axioms you need on this type are just this existence of these three functions.
Yeah.
But two functions.
To go over this again, you just write this code.
Yeah.
Auth, like when it is compiled for the prover, auth and unauth are being interpreted this way. When you compile it for the verifier, auth and unauth are being interpreted this way, and you get these.
No, but that's what I don't understand. So when you combine for the verifier, the unauth,
Yeah.
it needs to have that both serialization of A and the hash rate. So because the way you describe how unauth works, so on the
Right.
second column, it reads the serialization of A.
Yeah.
Whereas for the verifier, the A auth type just consists of a digest of A or a hash
Yes,
of
yes.
the serialization.
So it gets this it gets this like this serial. This is the serialization of it. I call D1 D2 as the serialization of the node.
Oh, okay. So
Yeah.
it'll be the after the hash.
Yes.
Yeah.
Sorry. No. Before the hash.
Before the hash.
Now this will hold. So D0 we know was this, right? So basically this will hold. Maybe I should have made this clear. And D1 D2, like what is the serialization of it, right? But yeah, I hope the basic sort of algorithmic idea of how this is working is clear.
That's fine. Well, just so can you just go to the next one, where you have the table.
Okay.
Yeah. So this one says that it reads the serialization of it, which is now the hash of this, not hash, it's just D1 D2,
D1 D2.
and compares its hash with its copy of the digest.
Yeah.
Okay. Okay. And deserializes. But how can it deserialize now?
Because we know how it was serialized, and we also know like that is sort of agreed
hash
upon.
one.
No, so D1 we are deserializing D1 D2.
There is
So you have D1, D2, you're just breaking it apart into.
Oh, no, serialization is just D1 D2 being.
Yeah, yeah.
That's
Right.
Okay.
Right. Yeah. So this won't be useful anymore, right? But I just want to give I just like this very nice construction. I think the idea of the paper in general is pretty nice. Okay. But here's the crucial part, which I am interested about. So to justify the correctness of their approach, they define a core calculus and show security and correctness. So they say that if you pass any unauthenticated data structure to the compiler, pass the Merkle tree binary tree to the compilers, they prove security and correctness properties for the generated prover verifier and the ideal. So the security property will say that the generated verifier, if the generated verifier accepts a proof P and returns the value V, then a simple ideal execution would also return the same value, or a hash collision might have occurred. Basically, it says the verifier cannot be fooled by an adversary with a bad value and a bad proof, right? Unless a hash collision occurred. And finally, the correctness property says that if the prover generates a proof P, the prover will generate if the prover generates a proof P and result V, it is going to be accepted by the verifier, and the idea will also return the same proof basically. Same value. Right. Now, Miller et al. Implement their language as a custom compiler frontend over OCaml 401, which does all the prover and the verifier transformation. So this compiler frontend does the prover verifier transformation. And basically, when we say that this frontend, this is sort of called the DSL, right? When we have this DSL, so we can have different frontends which will introduce different types for specific application. So that's a programming language term, right? Now the OCaml developers say that this compiler frontend API will evolve with the language, right? So now the problem that is that as the OCaml language evolves, like now the OCaml is at 5.3 or 5.4 right now. And now with every new version of the language, the developer would have to re-implement that compiler frontend, right? So this is more burdensome. Bob Atke, who's a professor at University of Strathclyde, proposed a solution for this. So he says that you can implement this Miller solution as a library within the language itself, within OCaml itself, right? So now I'm going to describe a programming language. Now this is not about the same like that previous knowledge. We don't need to know how the unauth and everything is interacting now. Now I'm going to basically describe how a library implementation, how basically we would implement the same solution that I just saw. Right. So Bob calls his library Authenticate. So now Authenticate is a module type signature which encapsulates type constructors and types of primitives required for implementing Miller's solution. So this type constructors basically you can imagine this as an interface, right? And now verifier and provers are going to be implementation instances of this interface.
Because that's how I thought. That's why they chose OCaml, because it allows this functors over modules.
So Miller initially did not do it this way. They did compiler transformations. So yeah, this is the way that you would actually do this in OCaml, right? So again, the way this is going to work is that Maybe I
And
can.
now you have two different implements of the module, right?
Exactly. So maybe I can skip a slide ahead first, is that you'd implement a Merkle module. This is again going to encapsulate all your types, definitions, and functions, and so on. And you'll instantiate with this authenticate type module, right? So this authenticate type can be either a verifier or a prover. When you instantiate it with the verifier, you'll get the verifier Merkle functions. When you instantiate with the prover, you get the prover Merkle functions, right? So let me just show how this is actually implemented. This is all the type signatures we have. So this is auth that says that it converts it takes an authenticated value, unauth, and so on, right? Now to do basically the proof carrying operations that we saw before, we have this concept of monadic computations. I won't describe how this is actually implemented, but this basically allows developer to write functions this way while the prover and the verifier streams are being manipulated behind the scenes, right? um, Finally, there are also these serialized, so the serialized, like people are asking, serializable questions.
So what do you mean by the developer to write in this way?
So the main point of doing all of this is that you want the developer to be able to write this code, binary tree code, and the prover
I see.
and the verifier operations being done behind the scenes
With those libraries.
with the library. So basically, this bind, unauth, this bind, and all of these things take care of that.
Everything has to happen inside the module because that is what you're going to change after the fact.
Yeah.
I think in the earlier thing, that's why you need a compiler transformation because the
Exactly.
slides would be different. But now they
Yeah.
look the same from the outside.
Right. Right. And we also have a submodule that does serialization. So people were asking, like, how do we know that the verifier and the prover are, like, how does the prover and the verifier know what to deserialize and serialize? So this submodule provides a framework for creating serializers and deserializers. And now so now basically we pass this, sorry. So now basically this unauth is going to have this sort of deserialization information, serialization and deserialization information for this arbitrary type. Okay, so basically this is how the fetch function is being implemented in using authenticate compared to Miller's solution before. And essentially, whenever we have unauth, an operation that is going to manipulate the proof stream, we have to surround this with this bind operator, and just some more scaffolding basically. Right, and this is how we would construct serializers for arbitrary objects. Right. So, for example, for this tree serializable function is saying that you should expect a sum type that is this left and right sort of thing, where the left value you need to use the string serializers and deserializers, and for the right value you need to use a pair serializers, which is in turn composed of like auth serializers and deserializers. Right. So this is sort of how serialization and deserialization functions are constructed for the prover and the verifier. Right. And this is basically all a developer needs to write. This is all the code that developer needs to write to implement the same thing using this framework. Okay. This is a bit more code than Miller's solution, but the guarantee sort of is that the type checker, the compiler will guide you in such a way that it is very hard to get this implementation wrong. And all the guarantees, future guarantees will say that as long as this passes through the compiler, you'll automatically get the security and the correctness guarantees that I showed you before. Okay. This is just a glimpse of how the prover module looks like. I'll just focus your attention on this line that is just concatenating the proof objects, proof streams behind the scenes. And similarly, this is how the verifier is implemented. I'll just focus your attention on this instance, which is doing the hash comparison with like hash equality check and we're calling deserialized to get future objects, right? So here we have And this is also consuming this proof stream. So this proof stream was T and PS, and eventually it is just returning PS. Right? So yeah, basically, and this is what an ideal module would look like. But basically, this is how this same solution is being implemented by in using this library definition. Now, why this is interesting for us is that we that the work that we did recently gives a formal proof of security and correctness for Authenticated. Okay. This is I haven't really talked about this, but yeah, we give this paper by us late last year from CCS 2025 gives a formal proof and security, proof of security and correctness of Authenticate, and we have fully mechanized all our results in the ROC theorem prover using the IRIS framework. Basically, Miller et al. So when I talk about a proof of security and correctness for this approach, you can imagine sort of a pen paper proof that says that, okay, if you take this program step and so on. We have sort of fully mechanized all these results in this theorem prover that makes sure that our proofs don't make any errors.
What is that IRIS then?
IRIS is a separation logic framework that has been implemented in ROC. It's not going to be very important for the things that I described.
And ROC is the same as the COC, right?
Yeah, it's been renamed to ROC, yes.
Oh.
Yeah.
It's what, sorry?
There is a theorem to go on
COC and
COQ COC.
So what is the relation between cock and rock?
Rebrand.
So they have renamed it ROC.
Yeah.
Okay. So now let me tell you why this approach is interesting. Why this is a paper, why people thought this approach was interesting, is that there's a lot of complexities in this proof. We have higher order functions. So reasoning about higher order functions gets a bit tricky. We have polymorphism, we have polymorphic types. So remember that the auth and the unauth function are implemented at the prover level. They are implemented for any sort of possible implementation. So they have to expect, so that's why we have polymorphism at the module level. We have recursive types. We have some state as well. Basically, there can be some global state in some modules. And we also have these abstract type constructors. So abstract type constructors is where things get especially tricky because maybe it's hard to describe, but yeah, basically abstract type constructors we also have that, and that these are things that make things very tricky.
So like something close. So like example, like even like this monad thing.
Yeah.
So to even say that the monad laws hold, that is usually something the type checker cannot prove for you. Right? So is that something you put it as an axiom, or that is also something you?
So what I'll show you very soon is that we verify the prover and the verifier implementations. We verify how the prover and the verifier are manipulating the monad once and for all, and that guarantee will carry over to whenever it has been instantiated.
But is there alright, but you have the full implementation of Authenticate, so that so it's not a
Right. So basically, this is how our approach looks like. Right. So now what I hope to do is that I hope to impart some sort of an understanding of. So I've given you some background. Basically, this is what our work is really about. I've given you some background about what we are actually verifying. Now what I hope would be interesting, like this is basically another part of the talk. So if someone was asleep before, I hope they can wake up. And now what I want to just show is that how you can actually model something that has an implementation that has all these features and verify that and give a formal proof of security and correctness for that.
Again, so for this, so the developer writes, they have to write their implementation of return and bind, right? Also.
No, the return and bind is also provided. So
Oh, is that provided by like
the return and bind are given by like these are given.
given by the Authenticate library itself. So
Yes.
so when you initialize the modules, what do you have to supply? You have to supply the types themselves. So what are going to supply if we write the function?
So the developer has to write this, has to give this. And
It's
now the
update of-
developer, this is basically says that this K will be replaced by prover or verifier.
Okay, yeah.
When this is prover, this will become a Merkle prover code. When this is verifier, this will become a verifier. And yeah, so basically this is how, so now what our goal is to say that whenever that module is being initialized by the prover and whenever that module is being initialized by the verifier and the ideal and so on, we want to prove similar security and correctness properties that I showed you before, right? So I'll just give you an overview of how the security proof looks like. So we will define this binary collision free separation logic called CFSL, which allows us to define these 4 quadruples, right? So the 4 quadruple is defined as so, where P is a precondition, a fact that needs to be true before 2 programs E1 and E2 run, right? So P is some precondition, some sort of a logical formula, and logical assertion. E1 and E2 are 2 programs that would run independently, so their execution doesn't influence each other in any way. We just use this to sort of relate 2 independent program executions. And Q is a post condition quantified over the outputs V1 and V2 of the 2 programs, right? So basically, we define this. What we'll end up saying is that the E1 is the verifier program, E2 is the ideal program, and we'll say that whatever, like, we'll prove the similar security property that I showed you earlier using the verifier and the ideal output. Okay. So, right. And then we show, so this is another property, we show that if a program is syntactically well typed, they will satisfy this sort of a CFSL judgment, right? So that, which means that if, say, this is a Merkle module, this Merkle module has some type tau, right? That means it has some type tau, that means that it has been accepted by the compiler, right? It will satisfy a CFSL judgment of this form. Both the programs are E and E. This is sort of the verifier and the ideal, like this end up being the verifier and the ideal programs, but they will satisfy some sort of a post condition that is like basically quantified over the type tau that is interpreted, right? What does this interpretation mean? Say we have this fetch code. Say we have this fetch code that I showed you earlier. This is the interpretation for this fetch code. Right? This is saying that this type, this is constructed by this is taking some argument paths, tree auth, and then returning a string option outcome. Right? I didn't really explain what this sort of means, but that's fine for now. Right? Basically, you can just see this, that this is the type of this function that is taking path, string, tree auth, and returning either a some string or a none string. Right? So the point is that when you give this, you will interpret this, you will write the meaning of this interpretation, like this interpretation would be defined sort of using structural recursion, right? So let me just explain how, so this is getting more, this is sort of more and more programming type theory sort of primitives. Basically, okay, so let me just try and go through this. So recall that in our language we have these abstract type constructors, apart from our regular types like string, booleans, etc. Right? So we have this colon a auth, right? So that means that this auth is a type constructor which is taking some type and returning another type, right? Now we want to create this type interpretations. So the type interpretation for basic types like booleans, ints, and so on is defined by that. Right? This is basically that saying that it is taking some value v1, v2, and returning some logical assertion prop. Right? And this is what auth constructor would be, that it is taking some type A, and returning some type A auth, and this is what that interpretation is going to look like. It is basically an interpretation from one map to another, or like it is a map from one interpretation to another interpretation. And basically, this is used to model type constructors like pairs, auth, etc. So basically, for proper types, so K is called kind. A kind is a So we have this notion of kind to differentiate between regular types like string, auth, etc., and type constructors. This is the kind for type constructors. Star or just a star is the type for is the kind of string auth option. So, okay. The type for any tau of kind k is going to be the interpretation for any type tau is going to be this. Right. This is just some. I'll just ask you to like accept this definition. This is what the interpretation is going to be for a type constructor, and this is what the interpretation is going to be when the type constructor is initialized. So this is going to be the interpretation for auth, A auth, and this is going to be the interpretation for tree auth, right? Why I showed you this is that I just want to give you some sort of an intuition that
Can you say once more about the difference between the types and the kinds?
so types are like you have like types are sort of initialized, right? So string, auth, boolean functions, these are types.
But you can also have abstract types.
Sorry, yeah, exactly. So abstract types are type constructors.
Correct.
For example, we have the auth type, but more familiar with the pair type. The pair types will have two arbitrary types for the first two locations, right? For the two locations. So a type constructor, so the pair is a type constructor, and type constructor have this kind, right? So we need all of this to define the interpretation of arbitrary type constructors and arbitrary types.
So when you say type constructors have this kind, so what do you
Yes.
mean by kind in that itself?
Kind is a sort of a noun.
Sort of a
Kind of like this is this sort of concept defined in type theory.
I see.
Like kind is a type is of a kind. That's what we say.
I see.
Like I'm not going to go into a lot of detail again here. But the point, like, let me just give you some examples of some basic constructors. A boolean is a basic type. It has kind star, and this is how this logical interpretation is defined for booleans. This says that it will take some value v1 and v2, and basically there exists some. If v1 and v2 satisfy this interpretation, we have this logical formula, which says that v1 and v2 are the same and they have the same type, same boolean. Okay. This is just a definition. For a pair constructor, this says that pair constructor is parameterized over two types. So the kind of a pair constructor is this. It will take one kind, take another kind, and finally produce another kind. Okay. Now this is parameterized over two different kinds, R and S. And V1 and V2 will satisfy that if so. First of all, V1 this assertion says that V1 and V2 are pairs, right? And sort of and basically W1 and W2, the first part of the pairs, will satisfy the interpretation of the first type, and U1 and U2 will satisfy the interpretation of the second type. Okay. This might be more interesting. This is how the auth interpretation is defined. So the auth this is the type A. Now this over here says that the first value v1, that is supposed to be the verifier value. The verifier value is going to be the serialization of the sum value A and its hash, right? And now A and V2 are related by this sort of you can relate A and V2 by this type A. So A and V2 are going to satisfy the interpretation of this arbitrary type A. Right. I just want to sort of build an intuition of how you can define relations, like how you can find the sort of define how you can build these sort of these sort of relations for arbitrary types. Okay. Now, what this is eventually going to be used to do is that we will have this, we will prove this assertion for the verifier module and the ideal module, right? We will prove that the verifier and the ideal module satisfy this interpretation for some authenticate type, which looks like this. Don't have to go through this. But there's some sort of a corresponding. The auth will have is going to have this type, unauth is going to have this type, and these types are parameterized over are parameterized over some abstract types, right? And to write interpretations for something like this, we have all that theory. For example, now for unauth, the unauth is going to have this type, and now yeah, I sort of just showed how you can. But yeah, basically, I've given you some sort of an intuition of about how this interpretation is going to be built using all those primitives before. Okay. And right, so what we do in our logic, what we what we do is that we showed this. We proved this theorem that as long as something is some program E is going to have type tau, this we automatically get this CFSL judgment. We proved this CFSL judgment for our implementation of the verifier and the ideal. And what we'll do eventually is that we will combine these two to have a security theorem, like the same security theorem as before, right? This says that the verifier if E instantiated with verifier accepts a proof P and returns B, then E instantiated with ideal will also return B, or a hash collision occur. Similarly, we'll have a correctness property as well. Okay. Yeah, so this is basically what our approach looks like. Okay. We also do so yeah. So now coming to like some more algorithmic intuitions, we do more optimizations of authenticate as well. We prove similar security and correctness properties for these optimizations. So you can imagine that proof stream, if you have the same value, like if you have serializations, if you have proof objects corresponding to same objects added multiple times to the proof stream, you can do some sort of a hashing, like caching strategy at the verifier and the prover to prevent adding multiple objects to the proof stream of the same kind. Okay. Right. Now we also I mentioned earlier that the authenticate implementation was emitting proofs of this kind, whereas the optimal proof that I showed you earlier was smaller, right? Now this is some sort of a limitation of authenticate that you have to larger client proofs and more computations. So what we allow someone to do is that one can manually implement verify the optimal algorithm. What this means is that someone can also just manually implement a fetch algorithm that does the prover operations, and separately implement the verifier algorithm that does the verifier operations, and just sort of manually check their correctness using some theorem provers, like using some formal verification. So far, the developer didn't have to worry about formal verification of their implementation. If they want a more optimal proof, they will have to do some formal verification.
So I did not understand like why Authenticate would produce that kind of a thing instead of the D1, D6 that you showed in the beginning itself, like D1, D6.
Yeah, so I showed you a second execution, and in that case, you saw that it was just simply the prover was simply adding a serialization of D1, D2. It wasn't being a very smart about like, okay, that in this case I don't need D2 or D5, for instance. So since this algorithm is oblivious to the actual operations and the actual data structure, we have authenticate will emit larger sort of proofs. Okay. We also try to see if Authenticate imposes additional cost. So authentic compared to Miller's solution. Miller's was a DSL. So this DSL is doing all of these operations at compile time, like substituting these operations at compile time. With Authenticate, you have these additional function calls that will say that okay, if this is unauth and there's a prover, then you have to go to the verifier unauth module to see how this looks like. The Miller solution is just substituting the inlining those calls at compile time. Right. So basically, we saw that with aggressive inlining, Authenticate's performance comes within 20% of lambda auth, and even for this 20%, there is some reason. Like this is what this sort of looks like. We implemented this for red black trees, and 100,000 insertions for prover and verifier. This is how the execution looks like over different tree heights. So the purple line is Authenticate, and the orange line is lambda auth. That's Miller's solution. To find the reason for this gap, we also tried to sort of did an ablation analysis over Authenticate to find what exact feature of Authenticate is causing more time. And yeah, this is some. Basically, we found that there is some very esoteric programming language reason, like some OCaml implementation reason why this is the case. Basically, if we had a better programming language, we would have performance very close to this blue triangle, which is basically the same as lambda odds. Okay. Now, to answer a very earlier question about can this be done only using OCaml, which I could have answered before. So, any language that implements any language that implements all of these features can also implement Authenticate in that. Okay. So for instance, Haskell, we can do this. I haven't properly explored if we can do this in Rust, but Rust or Go or these languages as well.
So in Haskell, how do you do this thing of having it's like having two different implementations for the same type for a type class of the same type or something. That's what the module thing lets you do in Panel. It's like Authenticate, it's sort of like a type class.
Yeah.
Haskell term. And like usually Haskell will only let you implement a type class once for a type. It will not let you implement a type class in two different ways for the same type.
I think there might be some different way of doing that in Haskell. I haven't actually looked at how this would be done, but
because this is usually like one of the things people say between OCaml and Haskell is the major differences. I mean, so like there are lots of people who will be proponents of type classes.
Yeah.
So nice. But this is one thing that the OCaml thing gets.
So OCaml, this is actually not a type class. So OCaml has
a module,
yeah.
But module is sort of like what a Haskell type class is. It's that it's a type which has to have this kind of an interface. And then you say this type implements this type class because this is how the interface is implemented.
So I think there is a different.
I mean, they're not the same thing, but they can often be used to do the same kind of thing. So you can have a type class like equality, and in principle you could have a module called equality with a signature, and a type could implement a signature. But now the thing is that it could implement it in two different ways, maybe just with hash equality and
right. No,
whereas in Haskell it will just be you implement it once.
Right. I see the differences. What you're saying, but I think this. So what I wanted to say is that I'm not very familiar with Haskell. I just know that. So basically, anything that will implement all of these features sort of is called to obey this sort of language construct called system F. So this is more core type theory, but anything that sort of implement all of that is sort of an instantiation of system F omega, right? So I won't go into this, but anything that can implement system F omega can implement this Authenticate solution. Right. Okay.
So we have a couple of minutes.
Okay, so yeah, I'm almost done. So this is some more algorithmic intuition about how to optimize authenticate. If someone was lost at the proof, they can come back. This is how the authenticate proof looked like. This is how the optimal proof looked like. Right? What's the difference here? Authenticate has D5, but D5 could have been computed using S5. Authenticate has D2, but D2 could have been computed using D5, D6. So Miller et al. They propose another compiler optimization that prevents adding these superfluous components to the proof. So they have basically identified some structural way of doing this, and what you get as a consequence is that you'll get smaller proofs by default. By if you just use their compiler optimization. Now we found so they don't properly prove correctness and security for this compiler optimization, and we found some bugs in their implementation. We fixed this bug, and we are also currently proving the security and correctness of this optimization. But this is sort of how this looks like. Instead of for the prover, instead of adding D1 and D2 immediately to the proof stream, you add it to a buffer, and you say that okay, I'm now going to D2, so I don't need D2 anymore. Okay. So now I'm going to D5, D6. It says that okay, now I'm going to S5. I don't need to add D5 to the proof stream. And this is what the final proof stream looks like. More interestingly, for the verifier will start with this. It will start with is D0 equal to hash of this D1 X1, where X1 is yet to be filled. So it will say that the left side is D1, the right side is some X1. Now it will know that X1 is X2 D6. Okay, and now X2 and D6 are the objects of the left and the right. And finally, it knows X2 is hash of S5. And then it can fill everything. And finally, just finally do the hash check only once, as we had shown before. Right, so this is another way of doing this sort of structure. We're still sort of doing this computation structurally. We have basically the smaller proofs, some optimizations. Okay, so I talked about this authenticate, which provides a safe and replicable way of implementing generic authenticated data structures without compromising on performance, while also providing support for implementing handwritten optimized functions. I then defined this collision-free separation logic, which helps us in verifying the authenticate module. Right now, we are also proving the security and correctness of the suspended optimization. It has some more complicated features, which takes a bit more time to model correctly. And we're also thinking about how authenticated data structures are actually used in all those cases, and how we can modify authenticate for them. So, for example, we found that I glossed over this problem of about how the verifier gets the correct commitment. So there are a lot of solutions that people implement for that, and we are also thinking how we can model those algorithms and features within Authenticate to automatically get proofs of correctness. Yeah, that's all. Thank you.
So in your that CFSL that judgment you were talking about.
Yeah.
So how will in the case of this Merkle tree, how will the execution that you were showing, how will the judgment typically look like?
I haven't showed that example over here, but so for instance, for the fetch operation, it looks like this. You can imagine for the update operation, it will be something else, and for the type, there's also this type tree and so on, right? So this is So this is how the fetch operations judgment looks like, and I didn't actually show this example later, but there is a separate interpretation for how this is constructed. There's a separate interpretation for auth. You can get a judgment like interpretation for tree, string, option, auth, comp, and everything, and basically construct this. in the end. Right? The thing really is that this judgment is oblivious of how the Merkle tree is implemented. All this judgment says is that whatever return value that we'll get will satisfy this, right? So the point over here is that we are not talking about if you correctly implemented the fetch operation. We only say that whatever the proof handling operations are going to be generated as a consequence, they are going to be correct. Right? So say you are implementing the update operation, and instead of updating the right comma left, like you get a query to update the value at right comma left. By mistake, you update right comma right. Like the algorithm implements right comma right. We're not going to verify the correctness of the update operation itself. We'll just make sure that the verifier and the prover sort of convince each other that they are proving and the verifying is correct. Yeah.
The question? If not, let's thank like then.
I got other tools,